Hi everyone, my name is Tamas. I'm a new Zen maintainer, so I've just been accepted as a maintainer last June, and I've been working on the virtual machine introspection subsystem within Zen. I work as a senior security researcher at a company called Novera, and before that I was in TU Munich in Germany, and simultaneously I'm doing my PhD at the University of Connecticut. So before I begin about virtual machine introspection, I figured I just show you guys a couple videos to get you guys up to speed of what this is actually about. All right, I still see people coming in, so there's a couple seats here and in the front as well. Grab a seat. No, I should be fine. I will try to speak into the mic. All right. So what we see here is actually Zen 4.4 running a Windows 7 VM, and what virtual machine introspection is about is actually being able to tell what's happening within that VM without having any software installed within that machine. So essentially you want to monitor the execution of, for example, what we see here is the execution of the Windows kernel when system calls are being executed. You want to do this from an external perspective for security reasons. You don't want to have your antivirus system within that machine, so you want to do it through the hypervisor. And you can already do that from Zen 4.4. So for example, these are all the system calls that get executed in that machine that's actually running live. So there's nothing happening within that machine, but there is a lot of things actually going on behind the scene. I'm trapping a lot of things within that machine that you can see on the left. And one of those things is, for example, I'm trapping heap allocations for Windows to reconstruct what objects are being allocated within that machine. So for example, if I start moving the mouse around, I will see IO allocations and high-level structures within that Windows kernel being allocated, which helps me reconstruct what's happening in there. So in case there is a rootkit, for example, I would be able to see its execution through the hypervisor. And this is what exactly it was built for. This is a drug-proof dynamic malware analysis system, which is open source, that lets you do this through the Zen API. And for example, you are even able to track what files are being opened within that VM without actually watching the disk at all. So these are just the objects that Windows allocates to represent what files it will access. So I just right-clicked on something, and these are all the files that Windows is opening within that VM, and I can tell this just by watching the execution through the memory and through the configured Intel virtualization extensions. So this is very handy, but this is just one use case. The other video that I want to show you is actually controlling this VM from an external perspective. So besides just watching this VM passively, you can actually control it through the hypervisor as well. So this is, for example, starting a process within that VM by hijacking the process manager that's running in there. So there was nothing special installed within that VM, and I was able to run arbitrary command external through the hypervisor. So effectively, you can have an external shell to that VM without having any username or password or software installed within that machine, and you can really do whatever you want. So for example, if I want to send that VM to a website, I can do that very easily. So this is a demo that I actually recorded for the Black Hat conference 2 weeks ago. There you go, Internet Explorer opens, and there it is. You can send that VM to any website, you can download anything and chain together commands and repeatedly run commands, and you can tell what the output of that was. So that is, in a sense, what virtual machine introspection is about. There's going to be another talk after mine that will touch upon a lot of the other use cases for what you can use this system for. But let's do a deep dive into what this is about. So there are really three main components for VMI: isolation, interpretation, and interposition. And these are the things I will be talking about in depth. So isolation is what I already mentioned, is being isolated from that ingest user space and ingest kernel so that your security application has that extra layer of protection and has that extra layer of view into the execution. And that is provided by Zen. Emulation kind of blurs the line, especially if it's buggy and you can break out, but fortunately that has been rare. But there's also isolation from the trusted computing base. So what I showed you, it was VMI running from DOM0, but on Zen you can actually separate that introspection component out into a dedicated machine through the Zen security modules. And that will allow you to isolate all of these things that might interact with potentially malicious code into deprivileged VMs as well. And the way this looks is essentially with XSM you can deconstruct what privileges are allowed to execute in what VM. And with that, you can actually create something that's a security domain, for example, or you can have multiple security domains, each having different controls over a subset of other VMs. This has been available since Zen 4.3. I actually had to patch Linux 3.8, the prev command driver, to allow this type of introspection, but this has been working for a long time. Unfortunately, XSM is not enabled by default, which is a shame because it's a really useful feature. It should be enabled by default, so well, that was in the default policy. I mean, you can create your own policy. No one should just run with the default policy that is just there as an example. But yeah, it's not tested as thoroughly because it's just not enabled by default. So we should probably do that.
Then minor correction is now tested.
It is tested. Excellent. Well, now this is wonderful. So let's enable it. So the second component, which I will just briefly talk here, is the interpretation is actually being able to tell what is within that VM. This is a huge topic. Many people wrote PhDs on it, so I just want to summarize it in one slide. Go check out libvmi. It's open source. It has a bunch of things in here. It's essentially doing memory forensic techniques live on a VM to reconstruct what's happening. What I spent the last year on Zen is actually looking at the interposition component of VMI, where essentially what we want to do is being able to interpose ourselves into the execution of that VM, step in, check what the state is, or even modify the state. And we can do this through the Intel virtualization extension, where there is a bunch of hardware traps that you can configure in the VMCS that will let the hardware trap into Zen when something of interest happens. Of course, these are very low-level stuff that happens, like, for example, moving into the CR registers, debug registers, or running a monitor trap flag, which is for single stepping. There's a bunch of these, and right now only the ones that are highlighted in red can be configured to trap into Zen, but technically all of them could. So these are just the ones that Zen currently has support for it. But these are already very useful, as you can tell. On Zen 4.4, you were already able to do what I just showed you in the videos. But there is a lot more possibilities if you actually enable users to configure what hardware traps they want to get notification on. The other one that is very useful is actually monitoring the memory usage of that VM through EPT, which is the Intel Extended Page Tables, where you essentially have two layers of paging. Of course, the first one happens within the guest from user space to kernel, or guest physical, and then EPT maps it from guest physical to machine physical. So in that second layer, you can change the access permissions to whatever you want. It's totally invisible to the guest. The guest will have no idea that you just marked that page non-executable or non-readable, and the violation will trap into the hypervisor. So you can really have read, write, execute trapping with some limitations. For example, there is no such thing as just writable page or just writable and executable, but there is such a thing as just executable page, so which is very handy. But there's a lot of more caveats in here that I have discovered while I started to work on some things which were in the area. One of it is this very interesting thing in the Intel SDM that deals with read-modify-write instructions, which usually used for mutexes, for example, or semaphores. How that behaves when you have access permissions set in EPT. Well, the Intel SDM, if you actually read this, says, an EPT violation that occurs during as a result of execution of a read-modify-write operation sets bit 1, data write. Okay, so it will get notification as, okay, write happened to that page. Better, it also sets bit 0. Data read is implementation specific, and for a given implementation may differ for different kinds of read-modify-write operations. So essentially, just think that guys just threw up their hands and were like, well, we have no idea what's going to happen. So if you want to get a notification when something is reading from that page, EPT is not necessarily going to tell you. You might get a violation, but the data is just not going to tell you that that happened. So, so this was an interesting discussion actually on the mailing list. I kind of find it hilarious, so I just wanted to highlight it here. Jean actually asked, why can the hardware report this characteristic right away? Well, the response was, well, there's a reason, but I can't really tell, right? Those are always helpful. Well, so I kind of was shoehorned into patching this, so we now just If there is a write violation, we just mark it as a read violation as well, because we might as well. We have no idea. Like, hardware doesn't know, how should we? So this one has been patched in Zen 4.5. A couple other things is that, for example, if you want to monitor memory through this system is, well, you hit a violation in the second stage paging, you need to relax that access permission, otherwise the VM is just going to keep hitting that page fault and it's just going to hang. So the way you do it is that, well, you get a notification through the EPT violation into DOM0, then you relax the permission, and then you enable single stepping, you let the vCPU execute one instruction, and then you reset the permission. So there's a lot of back and forth going on. And in fact, this was, the picture is not even that accurate. A lot more VM exits and entries happened there because things were done twice for no reason. But in Zen 4.6, this has very much been streamlined. So a lot of the duplicate VM exits and VM entries have been removed, so this is actually a quite smooth, optimized operation at Zen 4.6. Of course, there was one caveat that is not possible before Zen 4.6, is there is a race condition. If you have multiple vCPUs and you relax that memory permission on a page, and you single step one CPU, if you have another vCPU running at the same time accessing the same page, the access permissions have been removed, so the second CPU executing could go through without causing a violation and without you knowing, which is, of course, in a security scenario, is critical. So this is not possible to be solved before Zen 4.6. But in Zen 4.6, the alt P2M system has been introduced that helps solve this problem. So what alt P2M really is adding the possibility to define multiple EPTs for each virtual machine. So previously, what happened was in the VMCS, we just had one EPT pointer showing that, okay, this is the table that should be used for translation. Of course, the VMCS on Intel supports up to 512 page tables, just no one uses it. So with alt P2M, the Intel guys actually added the support for up to 10 pages, which is already very nice. So you can actually have, for example, one table where you have the restricted view, where you have removed permissions, so if someone is using that table, will cause violations, and then one where the permissions allow read, write, execute. And then if one vCPU gets a fault, you can just single step that vCPU, swap the pointer within that VMCS for just that one vCPU without affecting any of the others, so the race condition is gone. So this is really awesome, and I'm very glad that this made it into 4.6. It was, very last minute. There was freeze exceptions going on and a lot of drama, but it got in. I'm very happy about it. It's awesome. Again, this is what I just said, no race conditions. So once you get the interposition trap into Zen, you want to forward those events to a user space applications running in your security domain or DOM0. And this is a system that has been in Zen for many years before even I started looking at Zen. So how many people have even heard of mem event subsystem within Zen here? It's been there for 6 years at least. It has been there for 4.1 as well. So this has been there. It wasn't documented, and no one really knew about it. So this was, I think, an intern did it back at Citrix like years ago when it was just kind of forgotten. But it works. It's awesome. In 4.4, I didn't even touch Zen, and it was just working, and no one knew about it. So, well, there we go. Anyway, for 4.6, I cleaned it up because, well, it was in very poor quality code. In 4.6, we actually renamed it to VM event, and it has been cleaned up. And what this is essentially, it's a shared request response mechanism where you have a shared page with the VM. So the hypervisor has a shared page with the VM, and it's a ring buffer, and you can put events on it that the domain 0 will need to send a response to. There are two other systems beside the one using what I'm using for VMI that use this subsystem, which is a memory sharing and a memory paging subsystem, which unfortunately have been orphaned in Zen 4.6. The guy who was originally maintaining it couldn't do it any longer, so I'm very sad about that because I am using memory sharing, but it's not maintained, and it's going to be hard to decipher what's happening in there because there is really no tools out there that would demonstrate really how to use it. Anyway, so there are really many names here that it's kind of hard to keep track. So now it's a little less confusing because previously it was mem event and mem access and mem sharing and mem paging, and no one had any idea of which one was which, and the names were just all confused. So now we have VM event, which is the underlying API for this request response mechanism, and mem access is the one that controls EPT. And the monitor, monitor op dumctls control all the optional traps additional to EPT. So that's really the structure of what we have right now. So the header is defined in the public header. Now it's easily extendable and versioned, and there is no more hackery. Before it was kind of nasty. Things were named one thing and representing something else, and it was, depending on how you were using it, things were, you meant something else. So now there is no more hackery. It is very much straightforward on how to use it. And furthermore, in the response, when you have an event that Zen sends you, in the response to that event within this entire system, you can send a flag to tell Zen what to do with that event. So for example, you can trigger an emulation for one instruction, you can just enable single stepping, or you can swap the auth2 PM pointer. So there's a lot of optimizations in 4.6 that are now possible. So it's pretty awesome. Another thing that I was working on, I was hoping to get this into 4.5, but it got pushed into 4.6, is actually enabling this memory-based tracing for ARM. Because ARM also has two-stage paging, where the second stage is looked up that has hardware support for it. So it's essentially ARM's first virtualization extension, just had native support for everything that Intel took its time to implement. But anyway, so for 4.6, there is this mem access is implemented for ARM as well, so we can trace memory accesses. But what I couldn't find is really single stepping. Like if there are more ARM people here, I would love to talk to them, because honestly, I didn't spend too much time, but right now I don't see single stepping. So once you get a violation in the second stage page, how do you relax that permission, single step, and set it back? Because of course, alt-p2m is Intel specific. Right now, so there is no alt-p2m system for ARM, although it can be ported, because ARM just supports whatever page you give it. So there is not even the 512 hard limit on ARM, so alt-p2m could be ported to ARM as well. Anyway, so right now it can be worked around, but it's a pain. But more importantly, there is a lot of things in the TLB of ARM that were very interesting that I will talk about next. So to understand what the split TLB is about and what the problems there are, let's look at what the ARM mem access system actually has been, how it has been implemented. So first of all, the ARM page table entries have fewer software programmable bits available than what we have on EPT. And this is critical because on an EPT violation, when it happens, it tells you right away within that page table entry what were the mem access permissions. So those are the custom permissions you set through the mem access Zen API. On ARM, unfortunately, we don't have those bits available, so we have to store our custom permissions. Otherwise, we would not be able to tell if what was the default permission for that page table entry, so we would not be able to differentiate between artificial traps that we set, that we want to forward to the listener, versus the ones that happen just because that's how the VM is set up natively. So those mem access permissions on ARM are stored in a radix tree, separate from the page table entries. And whenever there's a violation, we'll look up what the permissions were by using the guest physical address as a key to see if there's anything there. Problem here, of course, is that ARM, when there is a fault, it only gives you the guest virtual address. The guest physical address is only given if you were doing a page table walk within the guest. So this is a problem because that means that on most cases, Zen needs to do a guest virtual to guest physical translation, which we don't have to do on x86. And this is where things get a little hairy, because what happens is, well, we have a native CPU instruction on ARM that does this for us, so which is really nice. We don't have this on x86. ARM did give an instruction where you can say, hey, I have this guest virtual address, please translate it to a guest physical address using whatever page table. How that instruction is implemented, though, is that it performs that translation as if it was a data fetch access. But what happened if we actually trapped an instruction fetch? Well, the in-guest translation will hit one TLB, which is the instruction TLB, which is, of course, the translation look-aside buffer holds these translation entries as a cache for speedy translation, but then hits the DTLB. So if there is one entry in the ITLB that differs from the DTLB, then Zen will have a totally different translation than what the guest has. And this is not, something I made up. This is a technique that has been used on x86 previously for implementing rootkits. So for example, the Shadow Walker rootkit has implemented exactly this mechanism to split the TLB and hide the malicious code pages from security software, because you can only see what's, the instruction is mapped to if you access it as an instruction fetch, which now with Zen on ARM, we really can't do. Flushing the TLB will not help. If the page table no longer represents that cached translation, that translation is gone, so you will have no idea where the rootkit page actually located. So this is a problem. There is an alternative way to trace execution. For example, we could inject instructions into the memory of the VM, similar to injecting breakpoints on x86, but this is not yet implemented. So that is something that I will be looking at. Also, if there is any other configuration for tracing execution on ARM securely, that would be interesting to see. But also, if there is someone here from ARM who knows more about the TLB than I do, that would be very cool to talk to, because, well, we spent a couple of weeks on the Zendevel list just trying to dig up manuals on, how the TLB actually is implemented on ARM, and there is not much information on it. So if anyone here can, I would be happy to talk to him about that. For x86, a couple of things. So yeah, the alt-p2m has been primarily designed to work with this new and upcoming Intel extension, which is the virtualization extension. And that's primarily designed for in-guest systems. So you can have like a hybrid VMI system where you have subcomponents in the hypervisor, some components within the guest, working in tandem with this system where it's all, have good performance and security. So this is going to be pretty cool. Also, getting something like this into KVM would be awesome, because, well, Zen is great, but a lot of people would like it in KVM as well, or other hypervisors. But I will be looking at the KVM thing next to get some system like that into KVM. So lessons learned. So this was my last year working with Zen. I ended up as being a Zen maintainer, but some things that were really annoying is why aren't we really using Git pulls on the mailing list? So most people just send the patches and don't specify where they branched off or when did they branch off. So you get a series, and even if you carve it out from the mailing list, you have no idea where you should apply. So if you try to apply it to Zen staging today, and that's not the point where they branched off, because they branched off a week ago, well, then you have to keep going back till you find a point where, okay, well, this is where I should apply it, and that's just a pain. So if people actually just create a GitHub account or whatever, put up your stuff into a Git branch where I can just set a Git remote, Git fetch, Git checkout, it's easy. It's 2015. Let's, this has been a solved problem, so start, pushing your stuff into Git. The other thing that was really painful, so I just went with the wiki on submitting patches to Zen. Yeah, it's great that we have that wiki, and it's very helpful, but a lot of time is wasted on the mailing list, on the review, doing dumb stuff like, oh, well, your patch obviously is not even going to build, so there you go. I just waited a week for you to tell me that, oh, it's not going to build, and review stop there, resubmit, wait another week, and then you get style issues. Oh, well, you have white spaces here, so resubmit. And then it takes a couple months before people actually start looking at your stuff and giving you feedback that's useful. So maybe giving access or some hints at least on how to do what type of testing you should do before you submit, and maybe giving people the tools to do style checks. Because I mean, honestly, spending so much time on white spaces, it's ridiculous. Anyway, so what I ended up doing is using Travis CI after a couple months of trying to build test everything manually on my laptop, and it's taking hours, and then things are just flying, and I missed the error. So I just started using Travis CI for at least compile testing series, especially for my series. I was touching x86 and ARM and the build system, so it was all over the place. So Travis CI really saved my ass many times. So it's up on GitHub if any newcomer want to give it a shot. It's okay. But on large series, it can really time out, especially the stop DOM. If you do make this stop DOM, not that thing, if you have 16 patches, each need to be compile tested, that will time out. Because on Travis CI, you have 1 hour to do everything. So it's, yeah. So it's okay. Maybe something more user-friendly or provided by the Zen community would help a lot for new people to submit patches and just, cut down on the review cycle, because a lot of time is wasted doing the review on things that should be trivial and should be checked for automatically. So, that would be very, very awesome. So thank you. This has been my talk. LibVMI and Druckwolf both are open source projects, both built on Zen. Please go check them out. And yeah, get in touch with me. I'm on Twitter. And if you have any questions, I will be happy to answer. Thanks. Cool. All right, if there are no questions, there is one. Okay.
Okay, I have a very maybe dumb question.
Yeah.
Okay, basically your work is pretty awesome, but I'm thinking in another direction. Suppose I'm a VM running in the cloud, but I don't want the hypervisor to know what I'm doing.
Yep. There is a new extension coming for Intel. It's called Intel SGX, which will let you create a memory enclave that's encrypted and is hardware guaranteed, so that you cannot.
Okay.
It's encrypted
so
memory.
Basically, that's based on the hardware. Is there any software approach to do that?
There is a couple. The More system might be one that Jacob Torrey pushed out that I would recommend checking out. But there is nothing right now by Amazon that I know that you could just tell Amazon not to peek into my VM. No, that's not possible right now.
Fundamentally, the software level hypervisor can always peek.
Right. Well, till we have SGX. Once we have SGX, that's going to be the solution for this, right?
Yeah, we can't virtualize that.
As what?
There are already exploits for SGX.
It's not even out yet. What are they exploiting?
There are a couple of guys at Microsoft Research working on that.
Yeah, it's Microsoft really the only one that has access to it. So if they're exploiting, their own stuff. Yeah, I think.
They know what they're doing.
Well, there's actually SGX version 1, and now there's SGX version 2 because they found so many problems in the first implementation, which is great. I mean, All right, so there is more stuff coming up on VMI, so stick around. Thanks, guys.